strong AI with artificial neural networks. It may sound ambitious, maybe mysterious. Once you see experiments with artificial neurons, you will understand how and why it works, what it can do and what not. I'd like to show you a few examples of neural network applications. We will begin first with visualizing the learning process of a neural network. It's both fun and very educational. We will then experiment with neural networks in Weka and see how the different components in a neural network influence its predictive capability. And we will end with a glimpse on a more advanced neural technology, which is called deep learning, for medical imaging diagnosis. So let's begin with visualization. We will use a very strong and successful AI platform made by Google called TensorFlow. This platform requires programming knowledge, not as Weka. However, there's a nice playground app which we can use for simple visualizations. Just go to playground.tensorflow.org. Here is our first neural network. As you can see, the first layer is the input layer where data comes in first. Then we have two internal layers called hidden layers with 4 and 2 neurons. And finally, the output layer. Here you can select different input data sets. Let's take this one, which is the simplest one. We will talk about the other parameters in a minute, but I want to focus now on how the learning is actually done. In the lecture, we talked about the ability of a simple perceptron to make a separation line or a number of lines in the problem space. So here we have two dimensions, x and y. Let's just imagine now, for the example, that x is glucose and y is cholesterol, LDL. Don't think about the units right now. We see that all the data points we have here, which comprise the training set, are from only two types, orange and blue. Let's just imagine for now that the orange patients are healthy and the blue ones are ill. Well, according to how these data points, these patients, are spread in the space, they can be easily separated by one separation line. So, let's see if the neural network will make this separation. Ready? 3, 2, 1, and we are running. I stopped the process after about 100 epochs, since, as you probably noticed, the separation into two regions happened quite fast. Soon it will not be that easy. What happened here? The learning process adjusted the synapses between the neurons in such a way that this separation line emerged. This process is somewhat similar to the other learning processes, such as the one we saw with decision trees. Here, instead of selecting attributes and threshold values for the nodes of the tree, we just adjusted the synapses. But the mode of action is the same. How is this adjustment actually calculated? This is a more complex mathematical process, which is not so important for now. But as you have probably figured out, the adjustment was done according to the orange and blue data points, the training set. The result of this adjustment, the result of the learning process, is the division of the space into regions, the orange and the blue ones. After this division was made, when a new patient comes in with a certain combination of X and Y, glucose and cholesterol, let's say 3 and 5 respectively, which is this point, the network will easily classify her as an ill patient. Notice that the data points we see on screen and the ones that were used in order to teach the neural network are only the training set. When we examine how good this network actually is, we need to run the data points of the test set through this network. If we click Show Test Data, we can see the test set and how nicely it falls in the colored regions. The ratio between the training set and the test set is determined here. You can see the success rates, which are actually failure rates, here, for both the training and test sets. The edges between the neurons represent the strengths of the synapse, when blue is a positive value and orange is a negative value. If you hover with the mouse on each neuron, you will see how it alone divides the space. The final division is a weighted mixture of all former divisions where the weights are the synapse's strengths. Actually, for such a simple dataset, for such a simple phenomenon, we don't need this mixture. Even one neuron will be enough. I will remove the second layer and the other 3 neurons. And as you can see, I get the same result. But what will happen if we study a more complex phenomenon, say this one? I will hide the test data and run it again. Not surprisingly, one separation line made by one neuron is not enough. The reason is that, as we saw in the lecture with the XOR example, we need more neurons in order to make more complex separations. I'll add another neuron. Now I have 2 lines, but they are still not flexible enough. Another neuron. A bit better, but still the error is a bit high. But if I add another layer, the result is much better. Let's see if this network is good enough to handle also this dataset. Not so much. Maybe if we add another layer and increase these layers, we will get better results. Oh yeah, fantastic. I hope now you can see the relationship between the architecture of the network and its predictive capabilities. There are many other parameters in this app. You can learn more about them here. And you can also just try to play with the parameters and see the results. Let's now see how we can make similar things on real data in Weka. For that, we will use again the heart disease UCI dataset that we also used in the last assignment about genetic algorithms. For those of you who haven't done this assignment yet, go to this address and learn about the dataset and its different attributes. This dataset is stored in CSV format, and therefore, in Weka, we must define the class label, the attribute that we want to predict, as nominal and not numeric. I show that one way to do so is here, under Filter, choose the unsupervised folder, attribute, numeric to nominal, and select the last attribute. And click Apply. Now, as we learned, we can very easily run a decision tree. And we got 78%. In order to run a neural network, we will choose it from the functions folder here under multi-layer perceptron. Let's just run it once and see the results. We received only 77%. We will click the hidden button where we can control the different parameters of the network. You can read more about it here. For now, we will turn the GUI, the graphical user interface, on and select one hidden layer with 3 neurons. We click OK and run it. Now, because I turned the GUI option on, I see the network itself. This is the input layer. These are the hidden layers. And I need to press start in order for it to start learning. I accept it, and as you can see, this time I got 94%. Much better than the perceptron with less layers and the decision tree. How lovely! In the assignment, you will get another chance to experiment with the neural network on other databases. But now, I want to move to another subject which we will only be able to have a glimpse at, but we cannot not mention it. This is called deep learning. This is where neural networks scale up a lot and use many more layers and many more neurons, as well as new kind of network architecture. It has been proven extremely successful in computer vision, and therefore also it is applied in medical imaging diagnosis. This is a wonderful survey, very extensive one, on deep learning in medical image analysis. It's publicly available on ResearchGate. You can see it has more than 1,000 citations so far, and as a survey it includes more than 300 references. From all the wonderful examples mentioned in this paper, I want to take you on a journey to see a few of the best ones. Deep learning is used for mammographic mass classification, as you can see in this paper. Also, leak detection in AOA tree segmentation. It reached human expert performance in skin lesion classification. It's good for bone suppression in X-rays, for diabetic retinopathy classification. In this case, it also won the Kaggle Diabetic Retinopathy Challenge in 2015. And what about segmentation of lesions in the brain? Got top ranking in 3 different challenges. A prostate segmentation work got top rank in PROMIS 12 challenge. Breast cancer metastasis detection in lymph nodes got top ranking and human expert performance in Chameleon 16. And noodle classification got top ranking in Luna 16. These are all just a few examples, and more and better applications are coming up every week now. So, I hope you enjoyed this practice session. Now let's do it hands-on in the assignment.